Hello everyone. Thank you very much. So this is sort of the summary, of the executive summary of my bio. I've been working with Python since about 2002. I'm now doing Python training and coaching and consulting and contracting, and Agile Abstractions is the name I do that under. My particular contributions to core Python itself have been in unit test and unit test.mock. The title of my talk today is Process Engineering, a Golden Age of Software Engineering. And I don't think that title appears anywhere in the talk, and I don't think the words a golden age of software engineering appear anywhere in the talk either. So I'm hoping that the content will justify this. And rather than perhaps give you more of my background and who I am, I thought I'd go on a bit of a journey, a bit like Travis, of take you on a little bit of my own journey with Python and how Python has changed and grown, and also how the software engineering community has grown and what this means for us as developers. And I think it means some pretty exciting things. So this is the Wayback Machine. This is the Web Archive. This is a snapshot of python.org in the 1st of January in 2002. Now, I don't know when in 2002 I started using Python, but if you'll note that Python 2.2 is out. The first version of Python 2, that was the version of Python I used. And we already had, we got there the good stuff like the new style classes, lots of great stuff. You'll see on the sidebar there, though, that Python 1.5.2 is still a thing. And at the time, there were many web hosting providers who were still using 1.5.2. So I remember writing code that was compatible with 1.5.2. But the earliest version of Python I used was 2002. And I got involved in programming with Python entirely by mistake, entirely by chance, pure serendipity. I was playing this play-by-email game with a bunch of people. We would email in our orders to a central server, and it would process all of our orders to explore and fight, and then it would send back our reports to us. And this happened once a week. And the reports were, of course, computer-generated. And because that only happened once a week, all of the interesting stuff was the sort of the diplomacy that happened in between. And so a bunch of us were in this alliance, and we thought, well, you know, we get these formats, we get these reports back that tell us what's happened, and they're a very regular format. They've been produced by a computer, so we could sort of parse this, and for things like our maps, we could share our map data. And I'd done a little bit of programming sort of prior to going to university. I actually ended up selling bricks. I was selling bricks at the time. I did that for 10 years. But this sounded great. This sounded like a great idea. And we'd actually just settled on Squeak, Smalltalk, as the language we were going to use. And somebody piped up and said, no, you should use Python. And so we said, okay. And that was how I started with Python. And I remember very much one of the things it kind of brought my mind alive. I did a simple implementation of Dijkstra's algorithm for pathfinding, so that with my sort of troops and armies, I had all this combined map data, this data structure, and I could say, find me the shortest route through the forests and the swamp to get over here, and it would generate my orders for me. And I long stopped playing the computer game and became passionate about Python. And the reason I really became passionate about Python, it was really about the community, and it was about it being open source. Because I was selling bricks, and suddenly I was really enthusiastic, really passionate about discovering programming and discovering Python and how easy it was to do things. And so I joined the community, I wrote articles, I wrote blogs, I released some code, please don't look at it. And also I was able to make some contributions back to the language itself. I helped with, I wrote some documentation. And it wasn't long before I decided, look, this is really what I want to do for a living. And I was fortunate enough in about 2006 to be able to, I joined a small startup in London. That was my first programming job. And the interview there was, that was the first time I'd ever met another actual Python programmer. I knew I was doing well in the interview when one of the interviewers said, "Oh, we had a real problem with Unicode, and I found the answers on the article you wrote." So I thought I'd probably get the job, and I did. And this was working in the London financial market, and we were building a spreadsheet that was going to take over the world. It was going to replace Excel. So you can see there we built a full spreadsheet application. And the idea of it was that, well, spreadsheets are the most widely used programming interface in the world. If you think about how a spreadsheet works, you have a bunch of data, and then you have formulae that operate on that data. So you'll have something like the contents of cell C6. That depends on the contents of cell A1 plus Z29 times 3. What this means is before you can compute the value of C6, you have to have already computed the value of Z9 and A1. And in order to compute those, well, who knows what else you've got to have computed. So what we have is a programming language. It's a pure functional language. It's expressions only that return results. And until you script it with VBA.NET, with VBA, there's no side effects. So you have a pure functional programming language where the order of execution is defined by a dependency graph. And that is the most commonly used programming language and programming interface in the world. And it's really quite an interesting programming language. And when you add VBA into the mix, it's sort of everything gets complicated. And there's been a lot of research, a lot of studies done, particularly in the financial world. And the end result is that within the margins of error, every spreadsheet has bugs. Every spreadsheet is wrong. So we wanted to create a spreadsheet that was fully programmable. You can see one of the formulae there is a Python list comprehension. So we had a combination of the Python expression language along with the formula language, and you have full access to the object model of the spreadsheet. So when you write formulae in cells, they get translated to Python code down there. You can add your own Python code. You can import stuff at the top. This is all a long dead and long gone project, but it was a beautiful vision. And this was some of the stuff that you could do with it, with an interactive interpreter. It was a beautiful place to work. And as a place to work, my first programming job, we followed the agile method of development, and this was sort of back in the days of about 2006. So it was full pair programming, it was full iterative development with sprints, it was fully test-driven development. We had customer representative, we had prioritization where the customers owned the priorities, but the developers owned the estimates. And we were very religious about this. We applied this sort of full XP for 4 years. That I was there. And what I really felt was that when I started my job at Resolver Systems, I taught myself to program. But what I really learned there was software engineering and thinking about software engineering and the processes involved in software engineering. So we've gone on a minor tangent about about what a spreadsheet programming language actually is. That really, actually, it's quite an odd language to program in. Which leads me to a lovely digression on what a programming language is. So what's the fundamental language that computers speak? Right at the heart, what language do computers speak? Assembly language, machine language is one answer. Binary is an answer that a lot of people give. And it's a trick question, because I always hope you'll get the answer wrong. So my understanding of the language that computers speak is the electromagnetic dance across etched silicon and wires choreographed by the beating of a quartz crystal at the heart of a machine. That's what the computer speaks, electromagnetic waves. And ones and zeros, they are an abstraction. They are a human representation of what the computer is doing. And it's a very low level. There's a very direct correspondence between the ones and the zeros and those electromagnetic waveforms. But the computer knows nothing of your ones and zeros. Those Oh, things that have been... What happened along the way in particular was the internet revolution. And if we go right back to the start of computing, computers were really, really expensive, and developers were cheap. So the programming languages that you use and the systems that they use, they were optimized to get every little bit of performance out of the computer. And if that made developers' lives harder, who cares? The developers are cheap, the computers are really expensive. So alongside, we had the commodification of computers, we had the massive growth in computing power, and then we had the internet revolution. And suddenly, people wanted to be able to produce systems, develop systems, and they wanted to be able to do it quickly. And doing it quickly is a huge competitive advantage. And along the way, computers got really, really powerful, and developers got really, really expensive. So if you could find a programming language, if you could find classes of programming languages that were way easier for developers to think in, to conceptualize, to reason about, so you needed fewer developers, and you could throw maybe a few extra machines at the problem. That was a great thing. We saw Google adopt Python as one of their official languages. It's interesting to note, though, that Python is a very general programming language. Round about sort of 2002, we were very concerned about Perl. That was our great competitor. Round about sort of 2006, we were very concerned about Ruby as our great competitor. And they're no longer in this chart. And the great success of Python has been in being this general purpose programming language with this very diverse community and a very diverse use cases. It's not all perfect. I spent a few years programming in Go. My ultimate conclusion was it's a tedious language. I'm sorry to all of you people who like Go, but it does a few things very right. Interfaces, the structural typing in Go, they're good. The fact that it's so easy to learn is good. And Go routines, their concurrency model, the actor model of concurrency with a scheduler under the hood, and you have true free threading. And in Python, people tell you, well, that's not what you want. What you want is multiple processes with inter-process communication. You write your code in C so you can release the global interpreter lock. And this is gradually, and in an ever-increasing multi-core world, this is gradually going to be more and more of an issue for Python if we look to the next 10, 15, 20 years. And there have been various approaches at various times to deal with this. One of the most recent ones, Larry Hastings' the gilectomy. Who of you have heard of the gilectomy? Some of you, a good number. So the Python global interpreter lock is the part of Python that ensures that only one thread of Python code will be executing at any one time. And that means that lots of the core parts of Python itself and Python data structures don't need to be thread safe, because you can guarantee that only one piece of Python will be executing at a time. And it makes all sorts of things simpler to reason about in Python. But it does mean that if you split your CPU intensive work inside Python into multiple threads, it's going to run slower because you're going to context switch between them. One of the big barriers to this is that if we want to move Python to a true free threading model, if we want to get rid of the global interpreter lock, we've got to have locking in all sorts of places. So Larry is made the most recent attempts to get around that, to put all the locking in the right places. There is some performance hit for the single threaded code. The big problem is Python reference counting. Python reference counting is how it does its garbage collection. It means we get deterministic reference counting. It has great advantages, but it relies on a lot of increments and decrements, and they're fundamentally thread unsafe. If two threads try to increment a value at the same time and the value of x is 4, they both read the value 4, they both increment to 5, and one of them will set the value back first, but you've just done 2 increments and the value only increased by 1. So so the reference counting would need to be thread safe. We'd need to lock around every reference count. So what Larry did was he thought, well, let's move the reference counting to a separate thread. But then when objects are freed, that blocks the reference counting thread, so we have to start passing objects back to their thread to free them, which is the right thing anyway, and it all gets horribly complicated. My conclusion, I don't know what Larry would think, is that what he's done is proved is that the global interpreter lock can be removed from Python. But in the presence of reference counting for garbage collection, it's an excessively hard problem. Thankfully, we now have, from people like the PyPy team, from people working on IronPython and Ironclad, they have produced and demonstrated that it's possible to produce a Python C API, because the big problem is we can't just switch away. We have all these mass of existing extensions which have to carry on working, which people depend on. But a couple of projects, the PyPy C extensions, Ironclad and IronPython, have demonstrated that it's possible to have a reference-counted legacy API for existing C extensions whilst having managed environment where the objects live with normal garbage collection. So I think, and if someone does that, and there are people looking at this, then Larry's work is basically good to go. So it's not an indictment on the gilectomy. Larry's done a lot of the work there. The next approach, which is current, is PEP 554. By Eric Snow, putting improving sub-interpreters in the Python standard library. And the idea is that you'll be able to, from Python code, instantiate a Python engine and set it executing in another thread. And actually, IronPython modeled this a long time ago, because IronPython, the Python engine, was built as a .NET object, and IronPython gives you APIs, access to .NET APIs. So you could create an IronPython engine. You could populate the modules dict with a whole bunch of pre-imported stuff, and then set it off executing code. And that's what Resolver 1 did, to have multiple documents open concurrently. It was great. So I'm really excited at the possibility of seeing this in the Python standard library. This is actually happening. There's a lot of progress. There's some really tricky questions around when you pass objects between these sub-interpreters. This works without getting rid of the global interpreter lock. You have a global interpreter lock per interpreter. So how do you handle shared objects? And something like the Go actor model of passing ownership seems to be the right way to do that. I should have talked to Travis beforehand and got a better slide for this one. This shows some of the amazing stuff that's happening in the Python data science world. It's another big driver of change and growth in the Python world. I'm seeing this in so IPython should be replaced with Jupyter, and there's a whole lot of other stuff that really ought to be there. But I'm getting a lot of inquiries for training, for cross-training people from Matlab to Python, and that's particularly from financial companies in London, which is really interesting. We really are seeing a migration into Python from other languages. What I see along with that is a lot of people, typically who have very good Python, but self-taught Python often, who are very smart at data science and know nothing about software engineering. Raymond talked about we can share dictionaries the same way we share spreadsheets by emailing them around. That's such a terrible idea, but it happens so often, doesn't it? Somebody emails you the spreadsheet, you modify it, you email it back to everyone who needs to know the change at the same time as somebody else who's done the same thing and now who's controlling the merge. And of course, this is a solved problem for us, isn't it? We have a whole bunch of evolved practices, workflows, processes, and tooling that solve a whole bunch of really important issues that are really going to bite you in the ass if you don't deal with them as soon as you're dealing with code. So one of my passions at conferences and the people I meet and the training I do is teaching basic sound engineering principles to data sciences, and I think there's a big need there. And it's great. We are seeing more and more people join the Python community, getting excited about Python, and we've got a lot to offer and to teach them. So, alongside the growth in Python, alongside the growth of things like data science, Python for web application development, we have seen the rise of Devops. Now you can see from this graph, this is a Google Ngram graph. The x-axis doesn't mean anything, I think, other than percent up to current. But you can see it basically started off becoming a thing in 2012. And in 2012, I was a software engineer, and Devops came out, and I was really skeptical. As far as I could tell, this was managers trying to get me to do system administration so that they didn't have to hire as many system administrators. And I hate system administration. So I resisted DevOps for a long time. On the topic of DevOps, Moshe Zadka, a friend of mine, a very intelligent guy, very smart guy in the Python community, he's just released this book, DevOps in Python. Infrastructure as Python, and he released it about a month too late for me to read before this talk. It would have been really handy, but I highly recommend this book. I'm about 15% of the way through it. And I guess what I want to do is, I've been converted to DevOps. I've come round to DevOps partly because of just the places I ended up working. I ended up working at Canonical for Juju, which is a DevOps tool written in Go. It's all about provisioning machines and orchestrating machines and encoding the arcane knowledge of how to do these things into reusable charms. And of course, there's a whole bunch of these tools that are very similar. And the next job, I ended up working as a test engineer on the Ansible Tower project, which is their enterprise product for running Ansible, another DevOps tool, across large systems. So me, highly skeptical of DevOps, ended up working on these tools. And what they introduced me to was this idea of thinking about systems and system design at a higher level than just writing the code and throw it over the wall. And that's where I think the real value in DevOps comes from, and we'll come to that shortly. There's disposable virtual environments is there at the bottom, because even though I'm only 15% of the way into the book, one of the really valuable things I picked up, which really I was kind of doing anyway, who's used virtualenv? Oh, quite a lot of you, but not everyone, or vmenv, the equivalent, or pyenv. Conda does a similar thing for you. They create a little virtual version of Python into which you can install your dependencies and then develop your code. So they provide a neat way of developing code. There's some use case for them in deploying code as well. But the great thing is, if you mess it up, they're disposable. It's just a directory. You blow it away, you create a new one, reinstall your dependencies, and you've got a new virtual environment. And Moshe's advice is treat them as entirely disposable. You don't ever need to do a pip install upgrade inside a virtualenv. Blow it away and recreate the environment. And the thing I love about this is, because dependency management, which we're going to get to, is such an issue for sort of quality software engineering. And by managing the dependencies in a virtual environment, knowing very clearly exactly what we have installed, what our dependencies are, I think is key to producing quality software. So this concept of disposable virtual environments, that was the first thing I really took from this book. So if we look at the rise of DevOps, if we look at the tooling available to us and the workflows that this enables, and I'm hoping to get a bit more specific. 5 minutes, in which case I'm going to jump ahead. Black is a code former that you need to be using. It embodies the Python, the code conventions from the Python community. The Python community does not always get it right. The @ symbol on the decorator, there was a huge flame war. Nobody thought thought Guido was right. It turned out to be a massive success. So process engineering is the thing I really like. And process engineering comes from the petrochemical industry, the branch of engineering concerned with industrial processes, especially continuous ones, such as the production of petrochemicals. And I have a friend who's a petrochemical engineer. He gave this snazzy definition. the magic of process engineering, you put in raw feed at the end, and you have to design the equipment and the processes under the constraints of pressure, heat, temperature, being able to use the byproducts as efficiently as possible so nothing is wasted, being able to carrying away. You design not just the end product, but you design the processes that produce the product, and you design the equipment to create it. And I thought this was a great metaphor for, he called them the alchemists of the modern era. I thought this was a great metaphor for what we do in software engineering. And so for me, process engineering in software engineering is the deliberate design of processes and workflows supported by tooling to enable the continuous and sustained delivery and maintenance of quality systems. And I think the place we've got to, the modern Python ecosystem, means that the how of software engineering is often now a solved problem, with what and why still remaining to be solved. We have a bunch of conventions, of processes that have come out of the community, that come out of the wider programming community. That means whether you're starting a framework, a library, a shrink-wrap desktop product, a web application you're delivering to people, or a web application that you deliver yourself, a platform, command line tools. There's a whole bunch of stuff we already know about good ways to do this. And the reason we do this is because we start with the end product and we work backwards. This is the CI/CD pipeline. I particularly like this because this is the Government Digital Services Singapore, and it's not bad. So this is one particular pass through the CI/CD pipeline. A set of processes, and the thing to note is that they're social processes as well as technological processes. Not everything has a technological solution, but the technological solutions support the social processes. So this is one workflow for the CI/CD platform. Note that it includes running functional tests, so deploy to staging, and build, deploy, and revert ought to be possible at the push of a button. Obviously now for our repositories and the platform, we're using GitHub. We can enforce some of our rules using Travis. I'm sure everyone is using Travis, Flake8, Black, Import Linter. These are tools that I hope you're familiar with. A shout out to travisci.org. I'm going very fast because I'm at the end, and I think there's a couple of slides that have some value here. The important stuff is the package building. You should now be using wheels, essentially the distribution building. You should now be using wheels if you're distributing Python packages. And the deployment. So Hinek is one of the captains of the Python industry in this space. He wrote this article. He outlines many of the tools. My takeaway from it was that none of the tools quite solved the problem as well as using requirements.txt. If we have a disposable virtual environment into which you've only installed the specific versions that you actually need and nothing else, you can freeze those requirements with pinned versions. And in an environment where it really matters that you're not using untrusted code, you can install from PyPI, but you can restrict pip to install from your own servers, from the file systems, even possibly keeping the dependencies in version control, all of which are important in many real-world situations. Running the tests, reluctantly recommend PyTest. I still love unit tests, but PyTest is just better. And this is the goal, isn't it? The deploy. We push a button. It's gone to staging. We take the build artifact that we ran all of our tests on the staging platform, the same build artifact, and we can deploy the same thing to production. And we know this thing is tested. But can we do these things at a push of a button? And how do we do these things? And these are the sets of tools that nowadays allow us to do these. Ansible tends to be the winner. Ansible is mostly about configuration management, and I really like orchestration thinking, because orchestration thinking, I think, matches how developers work with tools. Developers think about building systems, and this is why I'm a convert to Devops, is because this is how we think about systems. And this is thinking at the service level, the component level, the connection level. And many of the existing configuration management tools, they'll let you develop deploy the individual components, but will they let you specify how they connect up? Will they allow you to dynamically reflow that in production and change Postgres to a sharded configuration, add more Postgres servers, deploy more web application servers? And the answer is some of those tools can. And we codify the arcane knowledge of how to maintain our systems into things like charms, into Ansible playbooks, because anything that can be automated should. If you do a deploy and it goes wrong, if you can push one button to go back to the previous version, then you don't have to be afraid of deploying to production. If you can build a release from a single button, you don't have to be afraid of doing that. Build engineering is one subset of that. So I guess the takeaway is that I'm a reluctant convert to the world of DevOps, and we have such a wealth of extraordinary tools and experience available to us to do that. The slides will be available. I realize I rushed through probably the best chunk of that talk. If any of those tools you weren't familiar with, I'm sure most of you probably are, they'll be on the slides. Are there any questions?
Stop. Any questions?
Thank you very much.
Thank you.